In today's video, we're going to be talking about Newton's second law. After watching this video, you should be able to use and apply Newton's second law, and then be able to take Newton's second law a step further and be able to calculate the acceleration of an object using Newton's second law. So let's get right into it. Newton's second law of motion pertains to the behavior of objects for which all existing forces are not balanced. Okay, so now we're talking about objects where the forces are not balanced. And whenever when a force is not balanced, there's going to be an acceleration that occurs. Okay, a change in the object's motion. Now remember, acceleration doesn't mean speed up always. It also can mean slow down. But whenever there's an unbalanced force, you're going to have an acceleration. The acceleration of an object is dependent upon two variables. The first is the net force acting upon the object. So if you increase the net force, the acceleration increases also. Okay, so if you increase the net force, the acceleration increases. That's called a direct relationship. They are directly related. The second variable is the mass of the object. If you increase the mass of the object, the acceleration actually will decrease. Okay, so more massive objects are harder to accelerate. And that kind of makes sense, right? I mean, it's a lot easier to accelerate, say, a baseball than a bowling ball. Okay, I mean, the mass is what's going to be different on those two objects. Newton's second law of motion basically says that the acceleration of an object is directly proportional to the magnitude of the net force and inversely proportional to the mass of the object. And really, if you take all that gobbledygook and you put it into an equation, you get the very famous formula, F net equals ma, or mass times acceleration. Now, one thing that I really think a lot of physics textbooks do a disservice to in terms of this formula is F net is going to be either in the x or y direction. Okay, so you're looking at the net force in the x direction, and you're looking at the net force in the y direction. And you can have a net force in both directions, absolutely. But you're always going to be breaking it down into what are my net forces in the x direction, what are my net forces in the y direction. And a lot of textbooks and stuff never come straight out and tell you that, and so it leaves a lot of students in confusion. And I'll show you more examples of this as we go through the course. But F net equals mass times acceleration, and down below I tell you that F stands for force, which is measured in newtons, mass, which is measured in kilograms, and acceleration, which is measured in meters per second squared. Okay, so here we go. One of the areas of mistakes, and this is kind of what I was leading to in the previous slide, is that Newton's second law asks that you use the net force. Okay, you can't just use any old force that the problem provides. So a lot of problems will say, Johnny applied a 6 Newton force to a bottle of soda. What was the bottle's acceleration? And everyone wants to use that first force that they see. But obviously there's a frictional force in play, and that's going to kind of decrease the applied force. And you'll see examples of this in just a bit. But you have to make sure you get the net force, the overall total force in whatever direction that you're looking at, either in the x direction or in the y direction. Okay? So you must calculate the net force before you can use F equals ma, or else it won't work. You get the wrong answer. Okay. So there are a few formulas that are going to be useful for calculating the net force, and none of these are new as far as I remember. But if they are new, make sure you grab them because they're going to be important. The gravitational force, also known as F grav, or F, I a lot of times write it F sub g, equals m times g. Now, what is m? M is mass, okay, and that's measured in kilograms. And what is g? Well, g is the acceleration due to gravity, and in our class, it's going to be 9.8 meters per second squared. Okay? This is just from the last lesson. The frictional force, the force of friction, equals mu, which, what is mu? Well, that's just the coefficient of friction. Believe it or not, there are no units associated with it. It's just a number. And then the normal force, okay, which is basically a supportive force, if you will. It's the force that, like, a chair pushes back on you, or a table pushes back on your glass of milk that you have sitting on the table. These two formulas you'll use a lot to calculate the net force. Okay. Once you know the net force, then you can use Newton's second law, F equals ma, to calculate the acceleration on the object. Okay. And it's a beautiful thing when it all starts to work out. So I think one of the best ways to learn this is actually by doing example problems. Okay, now there's a lot of stuff going on in this picture, so let's kind of take it step by step, and we'll work through it. Here's a free body diagram of a box on some surface, and they tell us that the gravitational force is 100 newtons. There is an applied force of 20 newtons and a frictional force of 10 newtons. We don't know the normal force. We don't know the coefficient of friction. We don't know the mass, the acceleration, or the F net. Okay, so where should we start with first? Well, the thing I think I'd like to do first is I'd like to figure out the normal force, because I think that will be relatively easy. The normal force is always going to oppose the force of gravity, and basically, unless the problem states that the normal force is not strong enough to hold the box and it's going to break through whatever it is it's sitting on, the normal force will almost always equal the gravitational force. And so that will be true in this case, where if the gravitational force is 100 newtons, the normal force is going to also be 100 newtons. Okay. The second thing I think I might like to calculate is the mass. How can I figure out the mass of this object? Well, if you remember from the previous slide, one of the useful formulas we talked about was that the force of gravity, or F sub g, equals m times g. Well, they give me the force of gravity. They tell me it's 100 newtons, right? So I'm going to write 100 newtons here, equals m I don't know, but that's what I'm trying to figure out, times g, and g is always a given. It's 9.8 meters per second squared. And basically, if you do a little bit of manipulation here and take 100 divided by 9.8, you would get a mass of 10.2 kilograms. Okay, so we just got one of the things that we're looking for. We know the mass is 10.2 kilograms. Okay, now what should we do next? Well, I think what I might start doing is I might look at my forces in the y direction and my forces in the x direction. And let me change to maybe a different color for doing that. Let's see how blue shows up. All right, I guess it's not too bad. So we have x and y. Okay, so what are my forces in the x direction? Well, I have an applied force of 20 newtons. Okay, and I'm going to call to the right positive. 20 newtons to the right, and I have a frictional force that's pulling the left of 10 newtons. I'm going to call the left negative, so I'm going to call that 10 newtons. Okay, so the F net in the x would be, what's 20 minus 10? Well, hopefully you're thinking 10 newtons. Okay, now let's take a look at our y forces. We have a normal force that's going up of 100 newtons, and I'm going to call up positive. Okay, you can call it up negative if you want. It doesn't really matter because you'll still get the same answer. And I'm going to call down negative, and the gravitational force is negative 100 newtons. Okay, so what's 100 minus 100? Well, it's 0, right? So F net in the y direction is 0 newtons. So we have really nothing to worry about here. Okay, our net force is only going to be in the x direction. Okay, so our F net is going to be 10 newtons. We just figured that out. And what direction will it be in? Well, you could put positive 10 newtons, or if you want, you could just write to the right. Okay, it's to the right. All right, so now we're starting to cruise along here. What is the acceleration of this object? Okay, well, that one I think I'm going to be using Newton's second law. And let me change to maybe, well, let's do black. I guess I rarely do black, so let's see here. F net, and this is what I was talking about. What is the net force that we're talking about here? We're talking about the net force in the x direction. Okay, and we calculated that right here. F net x equals m times a, right? Well, what is the net force in the x direction? Well, we found that to be 10 newtons equals the mass, which we calculated already, is 10.2 kilograms times a. Okay, and basically, once again, I'm just going to leave this algebra for you guys to do. What is 10 divided by 10.2? I get 0.98 meters per second squared. And you can check me on that, but I'm pretty sure that's right. Okay. Now we have one last thing to do, and that is to calculate the coefficient of friction. Right? Coefficient of friction. In my lesson on friction, I told you guys, and I'm going to write this up here. Hopefully you can see it. That mu, do my best to write mu as best I can, is basically the force of friction divided by the normal force. It's just a ratio. Okay, well, do I know the force of friction? By golly, I do. It's 10 newtons. Divided by, do I know the normal force? Hot diggity, I do. It's 100 newtons. So what is 10 divided by 100? I believe that is 0.1. And remember, the coefficient of friction actually has no units, and you can actually verify this through the math. The newtons here both cancel. Both of these ends just cut each other out, and so you're left with just a numerical value. So it's 0.1. That's how you solve one of these problems. It is a little complex, it's a little intimidating because there's so many blanks, but you just kind of methodically work your way through by figuring out things that you can figure out, and then all of a sudden you have all the pieces of the puzzle and it's done. Okay? Once again, I just want to revisit this misconception, because now we're getting back to where it'll show its ugly face. An object does not need a force to keep moving. Okay, an object does not need a force to keep moving. Okay, and that's something a lot of people, and I myself too, struggle with, think is not true, that a force must be present to keep an object moving. Well, it's just not the case. Forces cause an acceleration, not a velocity. So forces cause an acceleration, so that is a change in velocity. Okay, and my example of this would be, let's say you go sledding. Okay, and here's a sledding hill. All right. Once you get to this point and you're down here at the hill, you keep flying forward, right? And you would actually keep sliding forever unless what stopped you? Well, what is necessary to stop your sled? Well, it's going to actually be the force of friction. Okay, the frictional force between your sled and the snow is actually what's going to cause you to stop. And thank goodness it does, because if there was no friction, your sled would just keep on going until you hit the nearest object, basically. Okay, so forces cause an acceleration, which is a change in velocity, not motion. Okay, so try to wrap your mind around that one, because it's an important concept to get. Okay, so on to another practice problem, and this is dealing with a guy who's sledding, so it kind of ties in well with my sledding example from the previous slide. Let's do an exciting color of yellow. So Lee is sledding with his friends, and he becomes disgruntled by one of his friends' comments, and he exerts a rightward force of 9.13 newtons on his 4.68 kilogram sled to accelerate it across the snow. So he pushes his friend's sled. If the acceleration of the sled is 0.815 meters per second, and this is another way of just writing meters per second squared, just so you guys know if you ever see that, then what is the coefficient between the sled and the snow? Okay, so how you do this, guy, is I always start off with a free body diagram. I start off with a picture. Okay? I feel like a picture kind of helps make all this text become a lot less intimidating. All right, so what do I know? Well, this guy, he exerts a force, an F applied, a force of 9.13 newtons, okay? And we know that the mass of this sled is 4.68 kilograms, 4.68 kilograms. And the sled accelerates with an acceleration of 0.815, that's supposed to be a 5, sorry about that, meters per second squared. Okay, that's basically what we know. And we're trying to find out what is the coefficient of friction between the sled and the snow. So we're looking for mu. Okay. The first thing I recommend doing with this free body diagram is first putting in the force of gravity. Okay, so F sub g. The force of gravity is there. Now ask yourself, what other forces are present on this sled? Okay, what is touching the sled? Well, one thing that's touching the sled is the snow. So the snow must be pushing up on the sled unless the sled is like going towards the center of the earth. And we call that F sub n, or the normal force. Okay, so F sub g and F sub n. And my guess is that these two are balance each other out, because the sled, unless it's like slamming down into the center of the earth, is probably going to stay on top of the snow, right? So F sub n and F sub g, there they are. Now, what force is opposing this motion of pushing the sled? Well, that is the frictional force, right? F sub f. Okay, so now we've got our free body diagram set up with all of our forces present. Okay. Next, I think I'm going to figure out what is the force of gravity. Okay, and remember, the force of gravity is simply m times g, right? And so I can absolutely figure that out. The mass of the sled, they told us, was 4.68 kilograms. 4.68 kilograms times 9.8 meters per second squared. Put a point there. And if you do that, I get 45.9 newtons. Okay. So if I have a downward force of 45.9 newtons, guess what my normal force is probably going to be? If you guessed 45.9 newtons, you're a good man or woman. Okay, that would be correct. Okay, so now we know the force of gravity. We know the normal force. What else can we figure out? Well, I'm thinking we can use Newton's second law. Let me change pen colors here to something more exciting. That if we use Newton's second law, because I want to get this frictional force, because I think that's going to be the key to getting the coefficient of friction. How can I figure out the frictional force? Well, I'm thinking if I use F net in the x direction equals, now what does F net in the x direction equal? That's just Newton's second law. Mass times acceleration, m times a. Okay. So do I have an m? I do, 4.68 kilograms. Do I have an A? I do, 0.815 meters per second squared. Now, what does F net mean? Well, F net is basically the difference between F applied and the force of friction, right? So I can say F applied minus the force of friction equals this. Okay, and that's how I'm going to get my force of friction, because I actually know F applied is this number, right? 9.139 newtons. I'm just going to write that in here right now. 9.13 newtons. So if I do this math, 4.68 times 0.815, and subtract it from 9.13 newtons, I get a frictional force of, let me see here, 5.33 newtons. Okay, so now I have a frictional force of 5.33 newtons. Now, can we get the coefficient of friction? I think so. And the reason why I think so is because if you remember your formula, mu equals the force of friction divided by the normal force. And do I have both of those numbers? I do. One's here and one's here. So what is my force of friction? It is 5.33 newtons divided by my normal force, which is 45.9 newtons. And if you do that math problem, I get a coefficient of friction of 0.116. Now remember, there are no units for the coefficient of friction. It's just a numerical value, and that is it. That takes care of this video lesson. I'll see you guys next time.